G'day lads, in this video I'll walk you through how I built my NFL prediction model for this season in Microsoft Excel. Now it takes data from last season and updates it each week with new data. After adjusting for each team's strength of schedule and a home advantage for any game, it then produces probabilities for the money line, spread and total points, which you can use to compare against the bookmakers' odds for any upcoming NFL game. Now, if you would like to download the spreadsheet you see in this video, or you're interested in more content like this, then you can click the first link in the description to go to the Excel Lads Patreon, where you'll be able to download this spreadsheet, the college football spreadsheet I made with the exact same framework as this, as well as spreadsheets for other sports such as the NBA, soccer, MLB, and pretty much every major sport, where I go through my process and teach you how to use probability distributions to accurately forecast sporting events. To start, before building any prediction model, I think it's important to begin with a clear framework. For the NFL, my goal is to estimate the probability that each team wins the money line, covers the spread, or the total points is under or over a certain threshold. But achieving this requires more than just comparing win-loss records or using an ELO style rating. To predict scoring outcomes accurately, the model needs to understand how teams actually generate points. Touchdowns, field goals, extra points, and even rare events like safeties all have to be considered. That means analyzing both offensive and defensive strength, adjusting for context, and then simulating thousands of game outcomes to form full probability distributions. The first step is to import the data we need into Excel. Instead of manually copying team statistics every week, which is slow, error prone, and not sustainable due to the amount of time it takes, the entire spreadsheet is connected to the internet using Power Query here. Now, Power Query allows us to automatically import live data from websites like teamrankings.com and Pro Football Reference. This is where I get the data for this model, and I'll put those links in the description below, which include stats like team standings, touchdowns scored and conceded per game, as well as field goals for and against. Now, whenever the refresh all icon is selected in the data tab, the spreadsheet refreshes its connection with the internet and brings in the newest stats. This pulls in data for both the previous NFL season, in this case 2024 to 25, and the current one, 25 to 26. Which is important because I want the model to use last season as a stable baseline while gradually updating its beliefs as the new season progresses. And all of this information is going to be stored in this raw data worksheet I've created, which becomes the foundation of the model's calculations. Once the data is inside Excel, I can organize it into structured tables: touchdowns for and against, field goals for and against, games played, and league averages. I'll call this spreadsheet attack and defense ratings. These will later feed into the offensive and defensive ratings, which I'll have to calculate for each team. And this will be used to project expected touchdowns, expected field goals, and ultimately the game simulations. Next, I'm going to create a worksheet called Dashboard, which will be the center of the entire model. This is where we'll be able to select two teams and have the spreadsheet automatically run simulations to determine probabilities for the spread, total points, and money line markets. And later on, we'll also connect to an API so that these odds can be compared to the bookmakers in order to find value when pursuing this strategy, which the video entails. So with the raw touchdown and field goal data now organized, the next major refinement in the model is applying a strength of schedule or SOS correction. This step is crucial because raw scoring stats don't account for how difficult each team's opponents were. For example, a strong offense playing weak defenses in a season can look artificially elite, while a team putting up average stats against top-ranked opponents may actually be better than their stats reflect. So the SOS correction will ensure the model evaluates performance in the proper context so that we get accurate figures. The SOS values I'll use in this model come from Pro Football Reference. Again, the link is in the description for you to access that, and represent the overall difficulty of the team's schedule for the 2024 and 25 seasons respectively. I've compiled these stats in a worksheet called SOS ratings. Now, these values are incorporated into the model by splitting them evenly between offense and defense, a 50-50 allocation that keeps the adjustments simple and consistent. For example, the Arizona Cardinals had an SOS of 0.9 for the 2024 season. This means the Cardinals faced opponents that were on average 0.9 points stronger than a league average schedule. So they had a tough schedule. I'll then split this figure into a positive 0.45 for their offensive SOS, OSOS, and a negative 0.45 for defensive SOS or DSOS. This ensures teams that played tougher schedules during the season receive more credit on offense and at the same time an offset on defense. This process will be done for both seasons. And next, I've chosen to divide the SOS contribution for each team between touchdowns and field goals. So across the league in the 2024 season, I collected these stats by myself. The share between touchdowns and field goals was 59.7% and 40.3% respectively. So each team's offensive and defensive adjustments are therefore scaled by these proportions to influence their projected scoring outcomes in the model. For example, the Cardinals plus 0.45 offensive SOS becomes 0.597 multiplied by 0.45 divided by 6 because a touchdown is worth 6 points, which equals 0.0448. For field goals, 40.3% of scoring, the adjustment is equal to 0.403 multiplied by 0.45 divided by 3. Again, a field goal is worth 3 points, which equals 0.0605. So these calculations show that after converting opponent strength into scoring units, the Cardinals' offensive schedule difficulty increases their expected output by 0.045 touchdowns and at the same time 0.061 field goals per game. The defensive adjustments apply the same exact magnitudes in reverse. They subtract the equivalent SOS effect to reflect that stronger opponents tend to inflate points allowed. And these touchdown and field goal adjustments are then recorded in this table here so that they can be added directly to each team's 2024 and 25 offensive and defensive totals to create SOS adjusted statistics. So in 2024, before these adjustments, the Cardinals averaged 2.50 touchdowns per game. But now after the SOS adjustment, their updated figure is now 2.54. By the same logic, after allowing 2.30 touchdowns per game in 24, this number has been revised to 2.26. Of course, the same thing is done to the Cardinals' field goal statistics with the adjustment of 0.0605 calculated above. And we'll do that for both the 24 and 2025 seasons, which will capture the shifting opponent difficulty as the seasons evolve. Now that every team's touchdown and field goal stats have been adjusted for strength of schedule, we can begin calculating the attacking, ATT, and defensive, DEF ratings, which is, for myself, in my opinion, the most important concept in this spreadsheet. At its core, this step reflects something called Bayesian reasoning. Last season's performance acts as a prior belief about a team's offensive and defensive ability. And as the current season progresses and fresh data becomes new evidence, the model will gradually update its beliefs to become more accurate. Early in the year, the prior dominates, and later in the year, the new data takes over. The model accomplishes this through a 12-game trailing window where the weights shift naturally as the current season accumulates games. So in week 1 of the spreadsheet, I want 100% of each team's attack and defense ratings coming from the 2024 to 25 season, as that's the only data I have. By week 4, through a 12-game trailing window, 3/12 or 25% of that data will come from the current season, 2025 to 26, with the remaining 75% coming from the previous season. And then by week 13, the model relies entirely on the current season. So firstly, I'll walk through the concept of offensive ratings or attack ratings. Now, the ATT rating measures how strong a team's offense is relative to the league. So it's just the team's adjusted scoring rate divided by the league average. For example, after SOS adjustments, the 49ers scored 2.48 touchdowns per game in the 2024 to 25 season, while the league average was 2.55. 2.48 over 2.55 is 0.97, which is their ATT rating. Now, an ATT value below 1 means the team scores less often than the league average team. Above 1 means they score more than average. So of course, if you're a team, you want your attack rating to be as high as possible. And I'll repeat this process for field goals using the SOS adjusted data. Defensive ratings follow an identical formula. I just have to divide the adjusted scoring rate allowed by each team by the league average. So using the 49ers example again, their adjusted touchdowns conceded per game gave them a TD DEF rating of 1.14, meaning they allowed touchdowns 14% more compared to a league average team, which means they have a pretty bad defense. And as you can tell, a high attack rating is good, while a high defense rating, on the other hand, is bad. Once the attack and defense values are computed separately for the 2024 and 2025 seasons, the model blends them together using the 12-game trailing window formula I described previously to make ratings for each team. These attack and defense ratings become the foundation for computing expected touchdowns and expected field goals, which drive every simulation in the model, which of course we'll need to generate the probabilities at the end for the 3 markets. However, before we choose any probability distribution I just mentioned in order to model touchdowns, field goals, safeties, and extra points, we need to first check whether a home field advantage actually exists, and if it does, how big it is. Ignoring this effect would bias the model because teams clearly perform better historically at home compared to when they play away. This is seen in most sports, whether it's due to a crowd effect or them being less fatigued from travel. We just need to measure and identify how big this effect is so that we can implement it for any upcoming games. To test whether it exists, we can compare the home score and away score from each game. Because both scores come from the same match, this gives us a matched pair of results. And our question is, in the same game, do home teams usually score more, or is any difference just random chance? And to answer this, we can use something called a paired t-test, which checks whether the average score difference between home and away teams is meaningfully different to 0. So for example, if we find that home teams score 0.1 points more than the away side over the course of an entire season, we might attribute that to luck because it can vary. But if we find that they score 10 more points, for example, then we'll say, okay, this is significant. For our test, the null hypothesis states that home and away teams score the same amount on average, and the alternative hypothesis states that they do not. And for those not familiar with this statistics jargon, it means that if the data strongly disagrees with this idea, we can conclude that a home field advantage exists. In the 2024 NFL dataset, the results show that home teams scored an average of 24.1 points, while away teams scored just 21.9. That's a difference of 2.2 points with a 95% confidence interval from 0.59 to 3.96. And with a p-value of 0.00832, which is well below the 5% significance level, this allows us to reject the null hypothesis and conclude that a real statistically significant home field advantage exists. The difference corresponds to about a 10% advantage to the home side, so that's what I'll implement into this spreadsheet. To incorporate this into the model, I'll scale both expected touchdowns and expected field goals depending on who is at home in a new worksheet called Simulations. The home team gets multiplied by the square root of 1 plus 10%, and the away team gets multiplied by the square root of 1 divided by 1 plus 10%. So that if you take the home team multiplier and divide it by the away side multiplier, that gives the home side an advantage exactly equal to 1.1 or 10%. Now, lastly, before simulating a game between two teams, we need to assess the likelihood of them converting extra point attempts and scoring safeties. As safeties are rarely scored and the differences between teams converting extra points are often minimal, I have standardized these stats in this model. So using historical stats from the 23 NFL season, I've allocated each team an expectation of 0.03 safeties per game. And an analysis of the 2023 NFL season shows that following a touchdown, teams attempt an extra point of 90.2% of plays compared to 9.8% for 2-point attempts. And an extra point was successful 95.9% of the time, while 2-point conversions were only successful 55.1% of the time. Shortly, I'll build these conversion probabilities directly into the simulation so that every touchdown not only adds 6 points, but also triggers a realistic follow-up event, an extra point attempt or a 2-point conversion before the full match simulation begins. Our next goal is to translate a team's relative offensive and defensive strengths into an actual expected scoring output for a specific matchup. These expectations, expected touchdowns and expected field goals, act as the mean values of the probability distributions used during the simulations. To calculate expected touchdowns, I'll have the model multiply a team's attack rating with the opposition's defense rating and then the league average touchdowns per game. This formula reflects intuitive scoring behavior. Strong offenses score more, weak defenses concede more, and both scale according to the league's scoring baseline. So I've got another example. If the 49ers have a touchdown attack rating of 0.92 and the Cowboys hold a touchdown defense rating of 1.33, with a league average of 2.55 touchdowns per game, then the 49ers are expected to score 3.12 touchdowns in this matchup. Expected field goals follow the same structure. If the 49ers have a field goal attack rating of 1.21, the Cowboys a defense rating of 0.92 with a league average of 1.73, then the 49ers are expected to score just under 2 field goals. Of course, these expected scoring values aren't final predictors. I mean, when you think about it, how could a team score a fraction of a touchdown or a field goal? So instead, they serve as the mean parameters for the probabilistic distributions used in simulating the full game scoring outcomes. To simulate a full NFL game, we first need a proper probability model for each scoring component: touchdowns, field goals, extra points, and safeties. So instead of treating the expected values like fixed numbers, as I said before, we treat them as the means of an actual statistical distribution. So that way, every single simulation can produce a different number of discrete touchdowns and field goals, just like real games. A natural starting point for modeling touchdowns is the Poisson distribution, which is commonly used for modeling count data when events happen independently and at a constant rate. Under this model, the mean and variance are both equal to lambda, the team's expected number of touchdowns based on their expected touchdowns figure. In theory, if touchdowns follow a perfect Poisson process, the expected number of touchdowns and the variance around that number should be identical. But NFL scoring doesn't behave perfectly like that. Teams change strategies depending on the game situation, leading teams to slow down, trailing teams to get more aggressive. And of course, at different times, one team has the ball and others do not. So the assumption of a constant scoring rate across all situations doesn't hold. And because of this, real touchdown counts often deviate from what a textbook Poisson distribution would predict. But of course, we have the ability to test this to see if it's appropriate, or we need to change it. So to do that, I can run a chi-squared goodness of fit test. Now, this test compares the real touchdown frequencies from the 2024 season to the expected frequencies generated by a Poisson distribution with the same mean. On the graph, the red line shows the Poisson distributions plotted against the actual empirical touchdown counts. And from the graph alone, it's clear that the traditional Poisson model doesn't fit touchdown data properly. The real touchdown counts in the 2024 season were more tightly concentrated around the mean, especially with 2 touchdowns per game happening far more often than the Poisson model predicts. Furthermore, the variance of the real data is lower than the mean, which is something called under dispersion. For 2024, the league averaged 2.56 touchdowns per team per game. However, the variance was only 2.05. So that mismatch breaks the Poisson assumption that the expected value equals the variance, and the chi-squared test returned a p-value of 0.0164, which is below the 5% significance level. Statistically, this gives us evidence to reject the idea that touchdowns follow a standard Poisson distribution. So to model touchdowns appropriately, we need a distribution that allows the variance to be different from the mean, specifically a lower variance since real scoring is more consistent than the Poisson model expects. That's why in this video, I'll switch to the generalized Poisson distribution. The generalized Poisson adds an extra parameter called the dispersion parameter, which lets us adjust how wide or narrow the distribution is. Mathematically, the probability that a team scores X touchdowns is lambda 1 multiplied by lambda 1 plus X times lambda 2 to the power of X minus 1 multiplied by e to the negative lambda 1 plus X times lambda 2, or divided by X factorial. In this distribution, lambda 1 acts like the usual Poisson rate, the expected number of touchdowns, while lambda 2 controls the variance. If lambda 2 is greater than 0, the variance exceeds the mean over dispersion. If it's less than 0, the variance is lower than the mean under dispersion, which is our case. And if lambda 2 equals 0, the distribution collapses right back into the standard Poisson. This added flexibility is what allows the model to generate touchdown outcomes that actually match real NFL scoring patterns rather than relying on unrealistic assumptions. Once we have lambda 1 and lambda 2 estimated from the data, we can compare how well the standard Poisson and generalized Poisson match the real touchdown and field goal distributions from the 2024 season. We estimate the empirical mean and variance directly from the scoring data, and then I can run a chi-squared goodness of fit test to check which model fits better. And the logic is the same as before. If the model fits well, the observed and expected frequencies will be similar, giving us a high p-value. But if the model fit is poor, the observed data and expected frequencies won't match. We'll get a low p-value, typically below 0.05, meaning the model does not represent the data well. By running this test on both the Poisson and generalized Poisson models, we can formally decide whether adding this dispersion parameter actually improves the model. Comparing the two, as we saw earlier, the standard Poisson model for touchdowns returns a chi-squared p-value of about 0.016, which is below the 5% significance level and means it doesn't fit real touchdown data. However, the generalized Poisson model gives a p-value of roughly 0.52, meaning that we do not have enough evidence to say the model is wrong. Visually, the green generalized Poisson curve lines up much more closely with the histogram, especially around the peak values of 1 to 3 touchdowns. As a result, I'll choose to model touchdowns using this generalized Poisson distribution. Although when we run the exact same comparison for field goals, the story is actually different. Both the Poisson and generalized Poisson models produce high p-values, around 0.62 for the Poisson and 0.78 for the generalized Poisson, which means both models we can say fit well and neither shows a significant lack of fit. The two curves overlap almost perfectly on the histogram here, and in other words, the dispersion parameter doesn't add any meaningful improvement for field goals. So because of that, the standard Poisson should be perfectly sufficient for modeling field goals in this simulation. Now that we've chosen the generalized Poisson distribution to model touchdowns, we can set it up directly inside Excel so that every team's expected touchdowns value is turned into a full touchdown probability distribution. The first step is translating a team's expected touchdowns into a variance. Earlier we found that from the 24 NFL data, the league average team scored 2.56 touchdowns per game with a variance of 2.05. That gives us a variance to mean ratio of 0.8. In other words, the data is under-dispersed and the variance is only 80% of the mean. To preserve this behavior in the model, we scale each team's variance using that same ratio. So if Atlanta are expected to score 2.06 touchdowns, their translated variance becomes 2.06 multiplied by 0.8, which becomes 1.648. Once we have the mean and the variance, we can solve for the two parameters in the generalized Poisson model, lambda 1 and lambda 2. We can derive these values by solving simultaneously for lambda 2 using the definition of the expected value and variance of the generalized Poisson distribution. After some derivation, we can find the lambda 2 parameter by subtracting the square root of a team's expected touchdowns divided by their translated variance from 1. And once lambda 2 is known, lambda 1 is simply a team's expected touchdowns multiplied by 1 minus lambda 2. So we've got both parameters known and calculated for each team now. We can use these to compile the probability mass function, or PMF, for the touchdowns scored by each team. Using this formula here, I can find the probability of each team scoring each exact number of touchdowns from 0 through to 20, which I'll list down the column. From there, I'll convert these into cumulative probabilities. This is so that during a simulation, Excel can draw a random decimal from 0 to 1 and find the first cumulative probability that exceeds it. That tells the model whether the team scores 0, 1, 2, 3 or more touchdowns in that simulated game. This whole process turns a single expected value into a realistic touchdown outcome, one that matches the scoring behavior of real NFL games. From here, I'll go back into the simulations worksheet we created earlier, and this sheet will store everything the model needs for each team: their expected touchdowns, expected field goals, as well as the standardized expected safeties, extra point attempt rates, and success percentages that we defined earlier on in the video. Firstly, we can simulate a team's touchdowns by using the rand function to draw a random decimal from 0 to 1 and finding the first cumulative probability it exceeds, like I described previously, which instantly tells us whether the team scores 0, 1, 2, 3 or more touchdowns in that game. Next, I can model extra points, and this part is a perfect match for the binomial distribution because there is a fixed number of trials and each trial has a fixed probability of success. Once the touchdowns have been simulated, we know exactly how many post-touchdown opportunity a team gets. So for the extra point attempts, I can use something called the binomial inverse function, where the number of trials is equal to the number of simulated touchdowns, and the probability of success is 90.2%. In the same way as before, the rand function is used to simulate the outcome, and the number of 2-point attempts is simply the number of touchdowns minus the number of simulated extra point attempts. Now for the number of successful extra points, I can use the binomial inverse function again with the probability of success in cell W6, and for the successful 2 points, I'll use the 55.1% figure in cell W7. Lastly, I'll generate Poisson distributed field goal counts in Excel using the standard approximation, a binomial model with a very large number of trials and a very small success probability. By feeding a random decimal into binomial inverse, Excel can efficiently convert this into a realistic discrete field goal outcome. Here the number of trials will be 10,000 and the probability of success is equal to the expected field goals divided by the number of trials, and the rand function again returns the smallest number of made field goals whose cumulative binomial probability exceeds that random decimal. For simplicity, I'll model safeties using this same Poisson structure as field goals with an expected rate of 0.03 per game. I'll do this for both teams now, and a team's final score after regular time is equal to 6 times their simulated touchdowns plus 3 times their simulated field goals plus 2 times any safeties, and then adding all post-touchdown points from extra point kicks and 2-point conversions. Once both team scores are produced, they're compared to determine the winner. If the game is tied after regulation, I'll introduce a simplified overtime mechanism consisting of 3 possessions per team. Each possession's outcome is determined by a simple distribution, which I'll put in a table here, where a team punts 40% of the time, scores a touchdown 25% of the time, records a field goal 15% of the time, loses the ball 19.75% of the time, and scores a safety in the remaining 0.25% of occasions. Random draws between 0 and 100 in Excel determine the result of each drive, and I'll add in a condition that requires each team to have at least 1 possession of the ball in overtime. Overtime ends when one team has more points than its opponent, so I'll record the score at that stage as the final simulated score of the game. And of course, if overtime is not required, the score will be exactly the same as the regular time score. Now to the left in this simulations worksheet, I'll now run 5,000 simulated games using Excel's what if analysis and data table functionality. Each iteration recalculates random scoring outcomes for both teams and produces a distribution of scoring results that are simulated. From this distribution, probabilities for the money line, spread, and total points markets can be derived and displayed in the dashboard worksheet, and I've used the sum product function to do so. After running 5,000 simulations between Atlanta and Tampa Bay, for example, the spreadsheet shows that the Falcons have a 28.8% chance of winning, while the Buccaneers are the favourites at 71.1%. This reflects that out of the 5,000 simulations, Atlanta won 1,440, Tampa Bay won 3,555, and there was a draw on 5 occasions, meaning the 3 drives each on the overtime mechanism we had ended in the same result. To the left, I can convert these probabilities into equivalent odds. For the spread and total points markets above, the green highlighted cells are adjustable parameters that let you instantly see how the probabilities change for different scenarios, and you can compare these odds to a bookmaker's prices to identify value if you are pursuing this strategy. Lastly, I'll connect the spreadsheet to Yahoo Sports' free API in order to bring in pre-game and live odds from BetMGM into this table for each upcoming game. And to do this, I'll write blank query code to transform the JSON formatted data into a clean table, which I can then filter through in order to match the spreadsheet's model generated odds with those offered by the bookmaker. Before I wrap up this video, lads, I think it's important that I run through the limitations of this spreadsheet. I'll put it pretty bluntly so that there's no confusion. If this model was 100% accurate and was guaranteed to profit off of every inaccuracy offered by the bookmaker, then I wouldn't have an incentive to upload this video. Right now, the spreadsheet doesn't factor in numerous important variables such as quarterback and lineup changes, weather conditions, travel fatigue, and coaching decisions. Among others, these factors have the ability to change a team's strength quite significantly, and as a result impact the probability of all markets offered on the game. However, in my opinion, I believe this current spreadsheet to be a great baseline to build on. Once you feel confident in your ability to model scoring using probability distributions that are appropriate and that you've tested, run simulations and compare odds to find value, you can start layering this model to add in more complexity and as a result make it more accurate. Again, lads, if you would like to download this spreadsheet to use every week and perhaps change yourself to build off of, then you can do so by clicking the first link in the description. Otherwise, thanks again for watching the video. If you enjoyed it, please subscribe and leave a comment for what you would like me to do next.